If you recall, yesterday we were talking about the area under the curve, and we are using the discrete to model the continuous. The Riemann sum was our discrete sum. We dealt with we wanted to calculate area is equal to length times width, but the area was continuously variable. So we made the area constant for small changes in the width. Constant means we get to use multiplication, and for small changes in the width means we have a place to put the plus sign so we can create a discrete sum. Then we wrote this discrete sum as the continuous sum represented by the definite integral of f of x dx from a to b. It's weird to think about it this way. We're plugging in all the values from a to b into this expression f of x times dx. It's weird to think about it that way because there's nowhere to put the plus sign because the set a to b is continuous. It's a continuum. Nowhere to put the plus sign. There is no next real number like there is with integers. But that's our way of thinking about it. We go from the discrete sum as the model and the continuous sum, introduce this new notation, and we get a way to calculate it through the antiderivative. So we're going to take all the stuff that we did in chapter 3 and start doing that backwards. So the definite integral of f of x dx from a to b is capital F at b minus capital F at a, where f is an antiderivative of little f. Capital F is an antiderivative of little f. Capital F is an antiderivative of little f. We're only going to go through the most basic of antiderivatives because that's all we really need to get our point across. So our most fundamental antiderivative is we took the derivative, the easiest derivative that we know, the derivative of a power function, and we translated this into an integral, an indefinite integral by just doing an inverse of what we did before. To find the derivative, we multiply by the exponents, then subtract 1 from the exponent. So to invert that, we add 1 to the exponent, then divide by the new exponent. So we add 1 to the exponents, and then divide by the new exponent. So what do we need to do? We need to learn how to find some of our easy antiderivatives. We need to practice this so that we can find our easy antiderivatives and then see how that works in our fundamental theorem of calculus to tell us about area under a continuous function. So let's just practice finding some antiderivatives. Now, as instructions, just like the d over dx says, the d over dx says, take the derivative of whatever's coming next. If I want you to find an antiderivative, one way I can ask that is to put it into an indefinite integral. So here's the integral of f of x dx. We just leave off the from a to b part. That's an indefinite integral. So if there's no interval, from a to b, that makes this an indefinite integral. Or we'll say an antiderivative. This is going to be an indefinite integral, or find an antiderivative. This is one way I could ask that. So to find the antiderivative, we add 1 to the exponent, divide by the new exponent. There is an antiderivative. If you recall, the derivative is a linear transformation. So the derivative of a constant times a function is that constant times the derivative of the function. It would be really weird if the inverse operation was not also a linear transformation. That would really mess with our heads. So just like you would guess, antiderivatives also linear transformation. So the 5 is a constant multiplier, a constant factor. So we add 1 to the exponent and get x to the 8 over 8, and we just carry the 5. Keep the 5, divide by 8, x to the 8. Usually if it's just a 1 on top of our denominator, if it's a 1 in the constant, then we'll pull the factors of x up there and say x cubed over 3. But if there's something else in the way, then we write 5/8 x to the 8. I don't know where this comes from. It's just what we do. Some people will write 5x to the 8 over 8, and I think that looks weird. And I hope you do too. So you totally could write this as 5x to the 8 over 8. I don't know why that looks weird to me, but that looks weird to me. But x cubed over 3, since there's nothing else up there with the x cubed, that looks perfectly acceptable to me. Aesthetics is weird. Who knows? The antiderivative is a linear operator. This indefinite integral is a linear operator. Integrals are linear operators. So we can just do things a term at a time. The integral of 5x to the 7th is 5/8 x to the 8th. The integral of x squared is 1/3 x cubed. Any questions? Add 1 to the exponent, divide by the new exponent. Now, if you recall yesterday and even today, I talked about f being an antiderivative of little f. Capital F is an antiderivative. An antiderivative. This implies that there's more than one antiderivative. And for the fundamental theorem of calculus, we just need to pick one of those antiderivatives. So this should cause concern. You should be like, oh, dude, we can't be having more than one thing unless they're very similar. So let's talk about an antiderivative. This is why we say an antiderivative. Differentiation and integration are almost inverse operations of each other. Differentiation and integration are almost inverse operations of each other. but we can't make an actual inverse. We can't say that they are most definitely inverse operations. The reason is we can't make a one-to-one function. We can't make a one-to-one correspondence from where we started to where we end up. So for example, x squared is not an invertible function because 2 squared is 4, but also negative 2 squared is 4. So if we try to invert that, where does 4 go? 2 or negative 2? That's not a function. We have to make functions. So for example, grading is also not a function. Every percentage from 90 to 100 gets mapped to an A. But if I look at a grade of A, I can't tell what percentage it came from. There's a whole range of values. I don't know what it came from. If you have a 90, then you have an A. If you have an A, I don't know what your percentage was. All I could say was it was like between 90 and 100. Except those couple of semesters where I make some of the assignments worth 0 points, and then people get like 10 points out of 0 points, and then they have over 100%. In which case, I mean, shit. You win on that one. That's like when I mess up the grading and mark a wrong answer right. You know, like looking at your answer, like, oh, no, that's definitely wrong, but at least gave me credit for it. So you don't say anything. But if I mark something wrong that was supposed to be right, you know, I'll give me points. But then if it's like right next to the one where I gave you points, that you got something wrong on, you're like, oh, I don't know if I want to show him this. So what if he sees this one and just cancels them out? See, it's a self-correcting problem. So the problem is we don't have a one-to-one operation here. There is a case where many functions get mapped to the same derivative. Many functions have the same derivative. What function has the same derivative? What's the derivative of a constant function? 0, because a constant function is a horizontal line, the slope is 0. So here, the derivative of many different functions is equal to 0. So if we have a derivative that's 0, we don't know what it came from, but we do know it was a constant. So if the derivative of something is 0, we don't know what constant we started with, but we know we started with a constant. That's good enough. So we don't know the integral of 0 dx is going to be some constant. We don't know what constant, but we know it's a constant. Just a constant. I'll be kind of dismissive of it. It's just a constant. We don't know what constant, but it's a constant. We don't know what constant, but we know it's just a constant, so we're not that far off. So whenever we're finding antiderivatives, we want to write the general antiderivative. The integral of x squared dx will be an x cubed over 3 plus some constant that we can't find without additional information. And the way we mark that is we put plus c. That is the constant of integration. We're looking for functions. When I say what's the antiderivative of x squared, I'm saying what functions have a derivative of x squared. X cubed over 3 plus any constant will have a derivative of x squared. The derivative of x cubed over 3 is 3x squared over 3. The 3's cancel out, leave us x squared. The derivative of the constant is 0. So here we have an uncountable infinity of antiderivatives. Any questions? How's everybody okay? So differentiation and integration are almost inverses of each other. The reason that we can't declare them officially inverses is the derivative of every constant is equal to 0. So the integral of 0 is some constant that we don't know unless we have additional information. This is an iffy amount of space. I think I have to go move on. So let's grab our original question. What's the area under a curve and above an interval on the x-axis? Let's draw a picture of what's going on here. Our original question says, find the area under a curve and above an interval. So here our curve is given by y equals x squared. That's going to be our continuously variable length. I'm trying to find area is equal to length times width, but our freaking length is continuously variable. And above the interval, 1 to 3 on the x-axis. So I want the area under the curve and above the interval. The advantage that we have here is x squared is a function that we know the antiderivative of, so we can throw the fundamental theorem of calculus at this problem. So we do the thing where we make the Riemann sum, we let the number of rectangles go to infinity, and we get right to the definite integral. So the area is going to be the definite integral from 1 to 3 of f of x, which is x squared, dx. The fundamental theorem of calculus says we need an antiderivative of x squared. We could use any antiderivative that we want. So let's use the one where the constant is equal to 0, because we can choose which one we want. So I'm going to take x cubed over 3, that's the antiderivative. And we're going to evaluate this function at 3 and at 1, then subtract the results. Find the difference between the antiderivative at 3 and the antiderivative at 1. The notation for doing this is like when we're trying to plug stuff into the Leibniz notation derivative. We draw a vertical line afterward and say, evaluate this as x goes from 1 to 3. So this is a common notation for x equals 1 to 3. It's like one of those old credit card machines that none of you are old enough to have seen, so never mind. So this is notation for just plug in 3, then plug in 1, and subtract the results. So there's notation for taking 1/3 3 cubed minus 1/3 1 cubed. I don't want to write integral notation because I found an antiderivative. The integral notation says, find the antiderivative. So, okay, we've done that. So I can't use this integral and dx notation anymore. So I write the vertical line at the end, announce my intent to evaluate at 1 and 3, and subtract. So 3 cubed is 27 over 3 is 9. So this is 9 and negative 1/3. Our original function, the function that we are integrating, that's how we use it as a verb, we are integrating x squared. The original function that we're integrating is x squared. And antiderivative is capital F. The general antiderivative would be 1/3 x cubed plus c. But since we can choose which antiderivative we're using, let's choose the one where c is equal to 0. Also note we're doing capital F at B minus capital F at A. So whatever constant we use is going to get subtracted out anyway. That's why it doesn't matter which one we use. So let's use the easiest one. That's capital F at B minus capital F at A. And then there's the 8 2/3 that we get. Any questions? Is everybody okay? Any questions? Comments? Deep thought. I haven't justified why we would want to do this past the general, well, this is just multiplication. I want to do area is equal to length times width. That's just an application of multiplication. Area is equal to length times width. Anytime we're doing multiplication and one of our factors might be continuously variable, like distance is equal to rate times time, that's where we're going to have to integrate. If our rate was somehow x squared, you'll multiply that by the time from 1 to 3 or 2 units of time. That would tell us the distance traveled because our rate is in something like miles per hour and our time would be in hours. Miles divided by hours times hours gives us miles. So if x squared represents miles per hour and x represents hours, this represents miles. If our velocity is given by the function x squared, then between hours x equals 1 and x equals 3, we will travel 8 2/3 miles. If the length is given by x squared meters, then over a width of x equals 1 to x equals 3 meters, we will cover an area of 8 2/3 square meters. If the force that we are applying is x squared newtons, and we do this over a distance of x equals 1 meter to x equals 3 meters, then the work done will be 8 2/3 Newton meters or joules. Whatever application you have for multiplication is an application for integration. That's where I get all my applications for integration from and derivatives. I just look in the physics book and find out where they're using multiplication. And then I ask the physics professor, hey, can you explain this physics? And they start explaining physics to me and my eyes glaze over. And they're like, oh, you get it? I'm like, oh, yeah, I got it. Totally. And they're like, oh, can you explain it to me? I'm like, oh, no. And they're going to be, you're going to have to try to explain it to students. I'm like, oh, yeah, but I'll be fine. Don't worry. Don't worry. You know what I mean? Then I go to the chemistry professor. So I'm like, hey, where do you guys multiply? And then I find out where they multiply. I'm like, oh, that's awesome. They're like, well, do you want me to explain it? I'm like, oh, no, I got it. It's multiplication, right? And they're like, oh, yeah. All right, then. Good question. Then all we have to do is find out if that multiplication can happen at an angle. Because if the multiplication happens at an angle, then we just do the dot product. And everything's just vectors. It's all the same. It's all the same. Any questions? Comments? Yeah. A lot of our derivative tricks for finding derivatives, just using the nx to the n minus 1 thing, are also integral tricks for x to the n plus 1 over n plus 1. So if I wanted the integral, let's say, of the square root of x to x, I want to add 1 to the exponent, divide by the new exponent. What is the exponent in this case? A half. So we're just reading this as an x to the 1/2. These are green. X to the 1/2 power. So we're going to add 1 to the exponents. So 1/2 plus a half plus 1 is 3/2. And we'll divide by the new exponents. And then what are we going to tack on to get the general antiderivative? Plus c. Every time I say general antiderivative, like let's get that stupid auto insurance commercial. I think about Shaq. The general. Didn't Shaquille O'Neal do those ads? I've also tried to get Shaquille O'Neal to be a guest instructor, but you know, he's all busy and getting restraining orders. I'm just kidding. So a lot of the things that we do for derivatives, if we can look at powers of x, then we look at powers of x. If, for example, I have 1 over x to the third, how am I going to read this? What's this as a power of x? So when I got a positive exponent in the denominator, I can write as a negative exponent in the numerator. So I'm going to read this as x to the negative 3. Now I got to be careful here. We got to add 1 to the exponent. So negative 3 plus 1 is negative 2. And then we divide by the new exponent, so negative 1/2. And then we put plus c. For the general antiderivative. There is a place where this breaks down. If we look at 1 over x as x to the negative 1, then all of a sudden we can't add 1 to the exponent and divide by the new exponent. Don't write this down, because it's going to involve dividing by 0. I know you're in calculus now, but you're not qualified to divide by 0 until you pass this class. Once you pass the class, you can talk about dividing by 0, and it's fine. But right now, you're not qualified. If you get caught dividing by 0, they're going to be like, only need to see your transcripts. And if you don't see that Calc 1 with a passing grade, then like, oh, I'm sorry, you're not allowed to do that. And you get fined. Which means if you have enough money, then it just costs you money. So don't worry about it. So the problem here is that we can't add 1 to the exponent and divide by the new exponent. Don't write this down, because it'd be like, oh, x to the 0, oh, that's a constant. 1 divided by 0, oh, that's bad. Right, 1 divided by 0 is undefined. So this is not going to work. But that's okay, because we all remember what function has a derivative of 1 over x. Yeah. Natural log of x. The derivative of natural log of x is 1 over x. So not that. We have to go natural log of x. And what do we also have to put? We also have to put the plus c. There is a minor problem going this direction, but there's an easy fix for it. The function natural log of x and the function 1 over x have different domains. 1 over x only doesn't like 0. Can't plug in 0. Natural log of x also can't plug in 0, but also with natural log of x, can't plug in any negative numbers. So let's just fix that. So the integral of 1 over x is natural log of absolute value of x. Natural log doesn't like any negative numbers. And 1 over x does like negative numbers. They both dislike 0, so we're okay there. So the absolute value fixes the mismatched domains. Now you can find the antiderivative of any x to the n. Not comprehensive, but certainly super useful. How's that, okay? Antiderivatives don't show up till chapter 6. I completely jump over 4 and pretty much 5. And it's like, oh, you guys can handle it. That's because I have confidence in you. Plus, we just did derivatives. While that's still fresh, let's start going backwards, at least when we can. How's everybody okay? I know it's not. All right. That's the new thing. We can find antiderivatives. We want antiderivatives because that's how we operate with the fundamental theorem of calculus. That's how we calculate these definite integrals. We think of those as continuous sums that are modeled by these discrete sums. And the calculus game is still in effect. We model a continuous change with the discrete, a continuous sum with the discrete sum. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. I was just